In this question we're going to use a bit of lifting line theory, and we're going to look at an aerofoil, a symmetric aerofoil with a chord length C. So a symmetric aerofoil with a chord length C. C is chord length. The vortex sheet strength is given for that specific aerofoil. So we've got gamma is 2 alpha V infinity 1 plus the cosinus of theta divided by the sinus of theta. There we go. We're flying at an angle of attack alpha. So alpha is the angle of attack. We've got a free stream velocity, V infinity, free stream of far field velocity, an angle theta which runs from the leading edge 0 to the trailing edge theta. Right. So question A is show that the circulation can be given by gamma is equal to pi alpha V infinity C. So we need to prove that we can actually derive that. So we know that there is a relation between the vortex sheet strength little gamma and the circulation big gamma. So we need to first write that relation down. We need to know that. So that's going to be the integral across the entire aerofoil. So from 0 to C of gamma, which is some function of psi. Psi is the running Cartesian coordinate, running from left to right across the entire aerofoil, and we integrate along that length. So since we have our little gamma, the vortex sheet strength, in polar coordinates, we want to transform the integral. So we'll do that. And we can integrate, well, we have to do the transformation basically from psi to theta. So what we're looking at is a system which looks like that. We've got that half circle that defines the polar coordinates. There we go. Then we've got ourselves a 0 value here. There's a C value there. At the center there's of course C divided by 2. So that's going to be my radius C divided by 2. So I can draw a line like that and dash it down here. So this is my psi coordinate here. And that's for a given theta. So that theta and that psi are related in some way. Well, we know that the radius of the cylinder is going to be C over 2. So we can actually evaluate that psi must be that radius C over 2 minus this bit here. Right? Because we start here at 0 and then we move in the psi direction to some coordinate psi. So that bit here, from psi to C over 2, that bit is C divided by 2 cosinus of theta. Right, so that's how you can, if you don't remember the relations between the Cartesian coordinates and the polar coordinates, then we can do it that way. So we can evaluate what d psi is. Psi, my pen is not working 100%. So it's d psi d theta times d theta. So we need to take the derivative to theta, which will be the derivative of cosinus. But there is already a minus sign, so this is going to end up as C over 2 sinus of theta d theta. There we go. So we've got an expression for d psi. So now we can evaluate what our gamma is. And my gamma is equal to the integral. And we now don't go from 0 to C, but we go, theta is defined as such. So we're going from pi, from 0 to pi. 0 to pi. So c is now equal to pi. And this is still 0. The theta is equal to pi here. Right. Okay, so 0 to pi, substitute in that expression that we get for 2 alpha v infinity 1 plus the cosinus of theta divided by the sinus of theta. And we multiply that times d psi, and d psi is given as c over 2 times the sinus of theta d theta. So we can evaluate that integral, take all the constants outside, v infinity c divided by 2. Actually the 2's cancel out. Then we get a 0, we get a pi here, and the sinuses cancel out, so we get a 1 plus cosinus that we need to integrate. And if you do that nicely, you're going to get your result. Pi alpha v infinity times c. Right, so that was question A. That was for an aerofoil. We're still looking at that aerofoil. And question B, find an expression for CL. And CL is the lift coefficient of the two-dimensional aerofoil. So we need to evaluate what that is. And we know that CL, we know the definition for CL. CL is defined as L prime, which is the lift per unit span, divided by half rho infinity v infinity squared times c. Not times the surface area, but times c, because L prime is already per unit span, so it's already divided by a length unit. Right, so this is perfectly dimensionless. And now we need to evaluate what that L prime is. Well, we know that L prime is, according to Kutiakovsky theorem, we've got L prime is equal to rho infinity v infinity gamma. And so therefore we know that this is pi alpha rho v infinity squared times c. So we substitute that into our expression for CL. And what do we get? CL is equal to pi alpha rho v infinity, or it's rho infinity of course, c divided by a half rho infinity v infinity squared c. So we've got a c there that cancels out a v infinity squared and a rho. So all we're left with is pi alpha divided by a half. So dividing by a half is multiplying times 2, so we got 2 pi alpha, which you knew beforehand. So then, question C. Now we're starting to look at a wing where we're using this kind of airfoil. And so we've got a wing with span 2b. So we've got a span of 2b. It's manufactured with a symmetric wing cross-section at any point along the span. So we keep on using that symmetric airfoil. The wing is tapered according to the following equation for the chord line. So we've got an equation for the chord line given in the question, which is c of y is equal to c naught, which is a constant, minus 0.5 times y divided by b, c naught. With y is the coordinate running along the span, of course, and it runs from the root where y is equal to 0 to the tip where y is equal to b. So we have to calculate the planform area. So the question is, calculate the planform area S and the aspect ratio AR. So we want to get those two things. Well, let's start with the planform area of the wing, S. So we've got ourselves the chord length, but that chord length varies as a function of the span. So instead of multiplying it times the span, which you can do if your chord length is constant, we have to actually integrate it across the span. So we will start evaluating that integral, and it will not run, in this case, my span is given by 2b, not b. b is not defined as span, but here the span is defined as 2b. So we have to go from minus b to b. because y was 0 at the root, and y is equal to b at the wing. So we go from minus b to b of that function c of y, which was given in the question. Right, so we can evaluate that integral. So we've got this integral. My pen is playing up big time. But we go from minus b to b, c naught times 1 minus 0.5 y divided by b. So this is a linear equation that we can solve. And we're going to get, there we go, c naught y minus 0.25 times y squared, so that's a linear function. We still divide by that 1b, and then we evaluate this thing here. We evaluate that from minus b to b. And what we'll get out of that is 0.75 c naught times b. So now we've got S. Once you've got S, there is a relation between the aspect ratio and S. We've got the aspect ratio defined as 2b, that's my span, squared divided by S. And that gives me 8b divided by 3c naught. So that was question C. So we're gathering some information on building up an entire wing. Then we go to question D, and question D says that the wing also has a geometric twist in it. So the geometric twist is described as well. So alpha geom is defined as alpha naught minus 0.1 y over b times alpha naught. And alpha naught is a constant. Alpha naught is a constant. Right. Then we have to derive an expression for the total lift L prime on the wing when the plane flies at an angle of attack alpha and when the induced angle can be neglected. So we don't have an induced angle. That's important to realize. Right. So what do we know for this kind of wing geometry? Well, we've got an expression for the circulation using Prandtl's equation, Prandtl's integral equation. The only thing is there's not an integral equation anymore because alpha I could be neglected. So we don't have an induced angle, which removes the integral from Prandtl's integral equation. So what we're left with is that gamma, which is a function of y, is going to be equal to pi v infinity c, which is a function of y, that was given in the previous part of the question, times alpha plus alpha geometry, so the geometric twist angle, which is also a function of y. So we can substitute the definitions for c as a function of y, so that gives us a c naught times 1 minus 0.5 y divided by b, like that, and we multiply that times alpha plus the expression that we got in this part of the question, alpha naught minus 0.1 y over b alpha naught. There we go. So now we've got all this. This is, of course, all multiplied times those constants at the beginning. You have to realize that. Now, once we've got the circulation, we've got ourselves the lift as well. So we've got the lift per unit span, which is a function of y, of course, will be equal to rho infinity, v infinity, Kutaki-Yukovsky theorem again, times the circulation. We've got an expression for the circulation, so we can evaluate it. We know that the total lift, which we're interested in, the total lift on the entire wing, can be found by integrating the lift per unit span, so the L prime. So therefore L prime is going to be the integral of 2 times the integral from 0 to b. It's a nice symmetric plane, so we might as well go from 0 to b instead of from minus b to b. We just take twice the integral from 0 to b of L prime across the span. Right, so we substitute all of that in, and we're going to get twice from 0 to b pi rho v infinity squared c naught 0.05 alpha naught y divided by b squared Yes, I think I forgot two brackets. I think I forgot this bracket and this bracket here. So I need to include those. Okay, now I realize. So we've got 0.05 times alpha y. This is going to be squared. Then we've got minus 0.6 alpha naught, which is if we evaluated that term times alpha, we multiply that times y over b, and we've got some extra term plus alpha, so I'll continue on the next line, alpha naught plus alpha, and we integrate that across dy, and we of course have to close the big brackets. Right, so we need to evaluate that thing, which will then in the end give me 2 pi rho v infinity squared c naught times b of 0.05 divided by 3 alpha naught minus 0.6 alpha naught plus 0.5 alpha divided by 2 plus alpha naught plus alpha, and that's going to be your final lift. And each of these variables of course will have some value that you can plug in, but this gives you the relation quite nicely. Okay, so we go on to question E, and question E says some engineers perform experiments on this wing and managed to find the lift distribution across the span. So they are measuring, so they've got an L prime measured. So it's L prime, so it's a distributed force. And this is of course a function of y then. Do they have enough information to calculate the total induced drag force on the wing? Justify your answer. Now that's a fairly short question, depending on which equations you can remember. But if you know that the distributed or the induced drag per unit span, which is a function of y, is given as L prime as a function of y times alpha I as a function of y, then you quite quickly see that, you know, di is the integral of from 0 to b, and we again multiply this times 2 of L prime y times alpha I, which is a function of y dy. So clearly, if you've measured L prime, then we're still missing alpha I missing, or W missing. And W is my downwash, because I know that alpha I has got this relation that is W divided by minus W divided by minus W. My pen is not very good. Divided by the V infinity. So if I know W, I know alpha I, or if I know alpha I, then I can evaluate the drag. So no, they can't do it. That's the basic final answer to that. And that's the end of this question.